Euler's formula is as follows. E to the ix equals cos x plus I sine x, with E being Euler's number, approximately 2.71828, I being the square root of -1, and x being any real number. If you plug in pi, which is approximately 3.14159 for x, you get e to the pi I equals cos pi plus I times sine pi, and sine pi equals 0 and cos pi equals -1. So you end up getting e to the pi I equals -1. This could also be written as e to the pi I plus 1 equals 0. This equality is known as Eulers identity. This equation is very beautiful on account of the fact that it includes 5 constants: e, pi, I, 1, and 0. It also uses every form of basic arithmetic exactly once: addition, multiplication, and exponentials. However, before we can talk about Euler's identity, we have to prove its roots in Euler's formula. Here is the derivation of Euler's formula, which is e to the ix equals cos x plus I times sine x. Also, cos x plus I times sine x can also be written as cis x. First, set cis x equal to cos x plus I times sine x. Then, take the derivative of both sides. Only simplify one. Then substitute the negative for I squared. Then factor out an I of the right side. Divide both sides by cos x plus I times sine x, and multiply both sides by dx. Now you have two intervals, one on each side, and when taken, result in the natural log of cos x plus I sine x is equal to I x. Then on both sides you have e raised to it, and this results in Euler's formula. There is a second derivation that is more commonly used. This derivation involves a Taylor series, which is a series of where k equals 0 to infinity and x to the k divided by k factorial, and the series equals e to the x. However, I find the first derivation easier to quickly understand. There is also a geometric interpretation of Euler's identity and formula. When multiplying complex numbers, there is a phenomenon that rotates any point on the complex plane and multiplies it by the square root of the absolute value, the square of the real and imaginary, or also known as the distance formula. Any complex number on the complex plane using x and y as real and imaginary numbers can be represented with polar coordinates using r and theta, r being the total distance from the origin and theta being the angle from the x-axis, also in the complex plane. Euler's formula is a very good way to change between complex coordinates and polar coordinates. You can just use r times e to the xi is equal to r times the quantity cos x plus I times sine x. Any coordinate can be transferred. For example, 4 plus 3i is equal to 5 times e to the I 0.644, which is 5,0.644 in polar form. Let's say we had 4 points in the complex plane that made a square. 1 plus I, 1 plus 3i, 3 plus I, and 3 plus 3i. If you multiplied every point by 4 plus 3i, we get 1 plus 7i, 9 plus 13i, negative 5 plus 15i, and 3 plus 21i. If you put these numbers on the complex plane, you get the same square, the bigger area, and rotated counterclockwise. Since 4 plus 3i equals 5 times e to the I 0.644, multiplying complex numbers by 4 plus 3i happens to multiply the radius by 5 and add 0.644 radians to its position. There is an easily provable mathematical reason for that. Since all complex numbers, or even non-complex numbers, can be rewritten with r times e to the ix, multiplying two complex numbers is the same as multiplying r1 times e to the ix1 times r2 times e to the ix2. And it simplifies to r1 times r2 times e to the I x1 plus x2. This completely explains why multiplying complex numbers acts this way. You multiply by r and add theta.